then we'll look at some theory that will likely be very relevant in exam. Yeah, okay, I'm just going to get started now. So the first thing we're going to look at is divide and conquer. And I'm sure you guys know, like, the divide and conquer paradigm is essentially if I have a problem and I can split it into smaller non-overlapping subproblems. I'm assuming you're relatively familiar with this, so we're going to get started on this question, which is past exam question. It shouldn't be too bad, and let's just go through it together. Sorry it's a bit cut off, but it should be fine. Okay, so there's a d-kilometer road from Albertville to Computerberg, which Adam is driving along. Adam starts at Albertville and drives to Computerberg over n days. At the end of the arc day, Adam stays at a motel, AI, kilometers from Albertville. Adam drives in the same direction each day, so each motel is further from Albertville and closer to Computerberg than the previous one. At the end of day N, Adam arrives in Computerberg, and Adam would like to call some friends along the way. Unfortunately, the cell signal along the road is very poor. Adam's friend Blake lives along the road, B kilometers from Albertville. To get the best signal, Adam wishes to call Blake on the night when his motel is closest to Blake's house. So, just for example, if D is 300 and N is equal to 5, then we have our A, which is the distances of the motels, 90, 160, 200, 250, and B is equal to 210. Then Adam should call Blake on night 3 when his motel is 200 kilometers from Albertville and only 10 kilometers from Blake's house. Right? And what we're tasked with is to design an algorithm that runs in O log n time and determines the best night for Adam to call Blake. If there are multiple equal best nights, we can find any of them. So does anyone have any ideas on how we might do this? Anyone at all? Just any idea? Okay, that's fine. So I guess one of the hints here is a theme with a lot of divide and conquer algorithms, is we can use the time complexity to see if it is in fact a divide and conquer algorithm. Now this isn't necessarily true all the time, but if you do see a log n in the required time complexity of the algorithm in your exam, it's very likely that you will either be sorting or you'll be using binary search in some sort of a way. And even more specifically, if it's n log n, you could be using like both, or you could be sorting and doing something else. But if it's log n, there are very little algorithms that run in less than O of n time, and that run in O of log n, so you're almost certain that you will be using binary search here. So given that we're going to be using binary search, does anyone have any ideas about what we could possibly do? I'll just give you guys a moment.
Sorry, can I see the previous slide?
Oh, yeah, sure. Does anyone have any ideas now? Just don't be scared. Okay, that's fine. Yeah, okay, this is just something about the input. So I guess we've turned it more mathematical. So the input consists of positive integers dn and b, as well as an array A, which contains n minus 1 positive integers. And as we said before, each motel is further than the next, and that's just what that next line says, but mathematically. And we wanted to output the single integer index of any best night for Adam's ball Blake. What we can notice is that the signed distance between Adam and Blake on night I will be AI minus B. Do we agree with that? Yep. And this value is negative until Adam passes Blake, and then positive until Adam arrives in Compute-Berg. And this sort of a property is what we refer to as like monotonic. Essentially, like once it occurs, it's always true. So basically, as soon as he passes, it's always true. And this is the property of the fact that each motel is further along than the last one. So the best night for them to meet is either the last time this is negative or the first time this is positive. Do we agree with that? Yeah, so what that means is essentially the best time to meet is either just before the motel just before or just after where B is. And this makes sense because if I go any further, obviously it couldn't have been better than the previous one, and if I go any earlier, it couldn't be better than the next one. Do we agree with that?
Can we make the assumption that there's always going to be distance between them? That distance, like house will not be 0?
I don't think it specifically says that, but that's fine because in that case, well, AI minus B would just be 0, right? And then that has to be the one closest. Does that make sense? Well, there could be another one on it exactly, but actually couldn't because it is stated in the problem that you can't have that. Yeah. So the solution, as I said, doesn't involve binary search. So we binary search to find the largest I, such that AI minus B is less than 0. So the best night for them to meet is then either night I or night I plus 1, where night I is the one just before it, and night I plus 1 is the one either exactly on it or just past it. And whichever gives the smaller unsigned distance, or if either of the distances is equal, that will be the answer. Sorry. Yeah, so here's a representation of that first example. We can see that Blake's house is at, it doesn't say, but 210. And essentially, when we binary search, what happens? Well, we have A0 is 90, A1 is 160, A2 is 200, and A3 is 250, right? And we will set low to 0 and high to 3, or like n minus 1, I suppose. But in this case, it will be 3. And what do we know about binary search? Well, we take high plus low, divide by 2. And this gives us 0 plus 3 divided by 2, which is like 1.5. But we take the floor, which is 1. And so firstly, we check the the motel at index 1. So AI will be 160. And when we see this, we take the quantity AI minus the Blake's house B, and we find that it is negative. So because we find it's negative, well, what are we going to do?
Shift to the right.
Yeah, we search on the right-hand side, I suppose. Right? And we do this by making make low mid now. So low is now what the previous low plus high on 2 is. So our leftmost boundary is now 160. Does that make sense? And our high is still 250. So we have 1 plus 3 divided by 2 is now 2. We find that at index 2, we have this motel at 200. And we find that 200 minus 210 is still negative. Okay, so what do we do now? Same thing, right?
Yeah.
Same thing. Now we make 200 our leftmost, and 250 is still our rightmost. And then the next time we will have like 2 plus 3, which is 5, and divide by 2. Now we've come to the same one, right? And we know in binary search if we come to the same one, well, we've just found it, essentially. And the closest one is now either going to be 200 or 250. We can just check 200 minus 210 take the absolute value, that's the distance, or 200 minus 250, absolute value, that's the distance, and we find that 200 is indeed closer than 250. So 200 is our answer. Does that make sense? So a bit of an extension onto this question. Adam's friend Claire is driving in the other direction from Computer to Albertville. So let's say Adam was driving from this way, we now have Claire driving this way as well. They both start driving on day 1 and reach their destinations at the end of day n. On the ith night, Claire stays in a motel CI kilometers from Computer. To get the best signal, Adam wishes to call Claire on the night where their motels are closest together. So for example, we have Adam once again with the same hotels, and now Claire has motels at 70, 130, 180, 240, and this is distance from Computer, from the outside. Adam should call Claire on night 2, when his motel is only 10 kilometers from Claire's motel. Design an algorithm that runs in all of log n time and determines the best night for Adam to call Claire. If there are several equal best nights, find any of them. Does anyone have any ideas about how to do this? So two important things to notice. So once again, the time complexity is log n. So somehow we are still using binary search again. And the second important part is that Claire also has, like, her motels are only further away from where she came from as well. So this monotonic property still holds, right? Because both of them can only be further away from their origin than the previous time, I suppose. And this is what allows us to binary search. Once again, this is just the input format. So Claire's distance from Albertville on night I is CI, hence the signed distance between Adam and Claire on night I will be this value AI minus open brackets D minus CI. I'll give you a second to think about that, why that makes sense. And once again, this value is monotonic, right? So instead of binary searching whether this quantity is negative or positive, instead of binary searching whether AI minus B is positive or negative, we're going to look at if this value is positive or negative, and then the rest will be the same as the previous question. We just binary search, and it will either be I or I plus 1. Does that make sense? Yeah? Okay. I hope that question made sense. The next thing we're going to talk about is the Mass theorem. This will very likely, maybe, possibly, I don't know, don't quote me, but it might appear as a multiple choice question in your exam. So essentially, Mass theorem is just a way for us to describe the time complexity of divide and conquer algorithms. So let the factor at which subproblem number increases be A, the factor at which subproblem size decreases be B, and T of n be the solution of the recurrence. Then our recurrence will be T of n is equal to A T of n on B plus some f of n, where f of n is the time complexity of running whatever algorithm we have at each level of the recursion. At this point, you could, if you want to learn exactly the derivation, you can do it yourself, but for your exam purposes, you can just memorize this. So what we now need is what we call the critical exponent. So C asterisk is equal to log base D of A, and we call the critical polynomial n to the critical exponent. So we see that n to the c is equal to n log base b of a. This is actually equal to the number of leaves on our dividing conquer like recursion tree. So if f of n, we now have a couple of cases essentially of the Mass theorem. What we do this. If f of n is equal to O of n critical exponent minus some epsilon, then T of n is going to be precisely theta of n to the critical exponent. If f of n is equal to theta n to the critical exponent, then we have T of n is equal to n to the critical exponent times log n. And essentially what these two cases are is the first case is the number of subproblems dominates the recursion, and the second case is the subproblem and size have about the same contribution to the time complexity of my algorithm. And in the third case, we have f of n equals to omega of big omega of n to the critical exponent plus some epsilon. And for k less than 1 and some n naught, we have that a f of n on b is less than or equal to k f of n. So this regularity condition holds for all n greater than n naught, and T of n is equal to big theta of f of n. And in this case, the size of the subproblems dominates the recursion. Okay? Let's apply this. So I guess this is a possible multiple choice question that you might get. Suppose that T of n is equal to 2 T of n on 3 plus O of root n. What is the asymptotic complexity of T of n according to the Master theorem? Anyone have an answer? Anyone think A? No? Yeah, it's not A. B? Neither. So it's going to be C or D, right? And the way we solve this is actually we say that, well, the critical exponent is log base E of A, which is log base 3 of 2. And what's important is we are comparing f of n, which is the time complexity at each level, to n to the critical exponent. We see that log base 3 of 2, which is our critical exponent, is greater than 0.5, and 0.5 is equal to half, so therefore there exists some epsilon such that f of n is equal to O of n log base 3 of 2 minus some epsilon. And this falls into the first case of the Master theorem, just minus some epsilon, right? Because, well, this is my critical exponent, and then we compare to my f of n, right? Yeah, and we just apply the Master theorem essentially, and this gives us that T of n is equal to big theta of n to my critical exponent, which is n to the log base 3 of 2. Does that make sense, guys? Next, we'll move on to greedy. And I think one of the things that I don't know was in the exam last term that perhaps wasn't practiced in any of the tutorial questions was like, it was either an exchange proof or a greedy state of head proof. But here we'll go through both of them, because when you do, you will have some greedy question in your exam. And you can't, like, I guess you'll get some marks for saying the solution, but they will ask you to prove it. We're going to look at a problem you're very familiar with probably, which is activity selection, but let's just restate it. You are given a collection of n activities. The ith activity has starting time s sub I and finishing time f sub I with, of course, our activity starting before it ends. A set S of activities is compatible if no two activities in S conflict. In other words, no two activities can take place simultaneously. I guess you can only do one thing at a time. And the activity selection problem is to find a set of compatible activities such that the set is as large as possible. Does anyone have any ideas on how we might be able to run an exchange proof here? It's fine if not. But I'll give you some time to formulate maybe some ideas. So, with exchange proofs, what's important is essentially that, like the basic idea behind it is that if I had another optimal set of activities, I suppose, and I took one out and I replaced it in my greedy selection, it couldn't be any better. That's essentially what the exchange proof idea is, and we'll go through this one now. So, the greedy algorithm that I'm going to propose in this problem is to keep choosing the activity that starts last. You may have also seen as like keep choosing the activity that finishes earliest. These are actually the same. You can think about it like as time running backwards if you want. And that starts last, and then discard all activities which class with X, and recurse until there are no more activities left. So we claim there is an optimal set of activities that contains the activity that starts last. This will inductively prove the greedy algorithm. So if we imagine some set of activities and the last one is in, if we were to remove that one and the next last one is still in, and we can keep going with that. Sorry. That fixes it a little. Okay, so here's our proof. Let X be the activity that starts last. Consider any set of maximum cardinality S that does not contain X. Just any set, like anything, that as long as it doesn't contain X. Let Y be the activity in S that starts last. Since X is the activity that starts last, we have that Sy is less than Sx. Okay? But since Y does not conflict with any other activity I and S, we have that Fi is less than or equal to Sy is less than or equal to Sx. Thus, we call this set S plus is essentially S without Y, but with X. So S minus Y, union X. This still forms a valid set of activities. Yep. And moreover, the size of S plus and the size of S are exactly the same because all that we've done is remove one activity and added another activity back in. Exactly the same. And this is all we need. This already proves the claim. Does that make sense? Yep. So that was just an exchange proof. Yeah, you want to be mathematical, but I think they're pretty unstrict with like. If you get the main idea, you'll get most things. Next, we have the next type of proof for a greedy algorithm, and this is greedy stays ahead. For this question, we'll look at this cell tower placement. You're probably also familiar with it quickly. So, what's the problem? Along the long straight road from Baladonia in the west to Kaiguna in the east, houses are scattered quite sparsely, sometimes with long gaps between two consecutive houses. Telstra must provide mobile phone service to people who live alongside the road, and the range of Telstra's cell tower is 5 kilometers, right? And this is a radius of 5 kilometers. Our task is to design an algorithm for placing the minimal number of towers alongside the road that is sufficient to cover all houses. Okay? What is the greedy algorithm in this case? well, is the greedy algorithm not like I put it as far to the like I suppose east? Like I put every single one as far to the east as like possible. Like if I put one here, I want the 5 to be touching here, like the end of the red line to be touching here, and then wherever that next house ends, I go to the next house after that, and I put the end of the red line there. That's the greedy algorithm, and we're going to argue that this works. Let's attempt a greedy algorithm processing the houses west to east. So the first house must be covered by some tower, which we place 5 kilometers to the east. So we place the tower 5 kilometers to the east of this house. This tower may cover some other houses, but if it's more than 10 kilometers, we will eventually reach a house that is out of range of this tower. Then we should place a second tower 5 kilometers to the east of that house. We continue in this way until all houses are covered. At each house, you need to decide whether to place a new tower. This can be done in constant time by referring to the position of the most recently created tower, which can itself be updated in constant time if necessary. So therefore, this algorithm runs in all of n time if the houses are provided in order. And when we say in order, we mean from like east to west, or west to east, doesn't particularly matter. And all of n log n time, otherwise, because we will have to do a sort as a preprocess, and then run this algorithm. So this is the greedy method. We put that first tower there, put the second tower there, and the third, fourth, and fifth towers like this. You can see all the houses are covered, and we've used 5. We're going to argue that this is minimal. So where the exchange argument is akin to a proof by contradiction, greedy stays ahead is more similar to proof by deduction. So here's our proof. The claim will be that for all k, the kth tower in the greedy solution is at least as far as the kth tower in any other placement. And this claim will prove our thing, but we'll get to that. So essentially what this is saying is that the kth tower in the greedy placement is always further or equal to the east as the kth tower in any other placement. If this is true, then it would be impossible to cover all houses using fewer towers. Okay? So our base case is k equals to 1. So it is like induction, I suppose. Greedy places the first tower 5 kilometers east of the first house. So if an alternative solution places the first tower further east, because the range is only 5 kilometers, right? It would not cover this first house. So therefore, for k equals to 1, our claim is true. Yep? Okay, so but A is a solution, so it must cover all houses. This means the first tower of A can be no further east than the first tower placed by greedy. Now it could be exactly the same tower as greedy, that's no problem, but it can't be further east than that first tower. So we see that the claim is true for k equals to 1. We next need to prove the inductive step. So the inductive step, we see, firstly, we suppose the claim is true for some k minus 1. So a k minus 1, where A is the position of some other placement of the k minus 1 tower, is less than or equal to g k minus 1, which is the greedy placement of the k minus 1 tower. And we need to assume this because this is just how induction works. We consider then the kth tower. So greedy placed the tower at gk minus 1 and gk. So there is a house with gk minus 1 plus plus 5 is less than where the house is, and is equal to gk minus 5, which is the next kth tower, right, of the greedy placement. And I suppose like this diagram is precisely what that equation describes. So The alternative solution places towers at ak minus 1 and ak. Now, here's our assumption. This is really important. Assume that ak is less than gk. ak minus 1 plus, sorry, greater. ak is greater than gk. Then ak minus 1 plus 5 is less than or equal to gk minus 1. Right? This is from our inductive step. Plus 5 is less than h, which is equal to gk minus 5, which is less than or equal to ak minus 5. So you can see that the house h would not be covered by tower ak minus 1 or tower ak, because this is less than or equal to gk. So h is equal to gk minus 1 minus h minus 5 is equal to gk minus 1. So gk minus 1 is on this side of h, and it's on the very limit, and ak minus 1 plus 5 is less than or equal to that. Whereas we have h is equal to gk minus 5, but ak minus 5 is greater. Sorry, less than. And the problem with this is this case exactly here. These are our greedy placements, here and here, and assume that this is the furthest range of the non-greedy solution of ak minus 1. It goes to here, right? But we're assuming that this has to be further east, and this is not possible, because now this house here is not covered, right? Does that make sense? Yeah? So this is contradicting that A is a solution. And since we have a contradiction, because A is a solution, it has to cover every house, and this uncovered house contradicts this fact that A is a solution. And if you remember, so house H is not covered by tower AK minus 1 or tower AK, therefore our assumption was false, right? Our assumption that AK was further east than GK was false, because we arrived at a contradiction, so that means our assumption must be false. AK must now be less than or equal to GK. And this is exactly what we wanted to prove, right? So we have proof of the claim for all K, the kth tower in the greedy solution is at least as far east as the kth tower in any other solution. Yeah? We now use the claim to prove that no other solution uses fewer towers than the greedy solution. Okay, so we've proven this claim. We now need to use it to prove what our original statement is. So here's the proof that the greedy is optimal. Suppose the greedy strategy uses R towers placed at G1 through GR. Imagine there is a house H at GR minus 5. So it is precisely 5 kilometers west of the last greedy, the GR greedy tower, right? Which isn't covered by the previous tower. Therefore, H is greater than GR minus 1 plus 5. So the tower at GR minus 1 plus 5 does not cover this house, but the tower at GR does. From the induction, we know that for any other placement of R minus 1 towers, A1 through, I'm going to assume that says AR, we have AR minus 1 is less than or equal to GR minus 1. Therefore, house H can't be covered in the first R minus 1 towers of any other placement of towers. So at least R towers are needed, because if it's not covered in the first R minus 1, since it is a solution, we must take one more, and that's R minus 1 plus 1, is once again just R, so it's no better than the greedy solution. Yeah? Therefore, the greedy solution is optimal. So this is the greedy state ahead proof. It's essentially that, okay, we're better at our first choice, we're better at our K minus 1 choice, therefore we're better at our kth choice in every choice. Or better or equal to that, I suppose. I think the exchange proof is probably more, yeah?
For the inductive step, do you normally use contradiction to solve with the greedy algorithm?
It depends, but a lot of the time, yeah, it could be. You might need to use a contradiction. You could just prove it directly a lot of the times as well. But in this case, it depends on the question, I suppose. Yeah. Does that answer your question? Yep. I would say exchange proof is like usually easier and probably more common as well. Yeah. So. Yeah.
Is that like a way to tell which one is more? It's like questions that are more suited for greedy versus exchange.
It's hard to say. The thing is, like, every greedy can be proven in both ways, technically. But exchange is almost always easier. Yeah. And I think you'll see it a lot more as well. You may have seen it a lot more as well. I'm not sure in your problem sets, something like that. Okay, that's greedy. We're going to move on to our next topic of flow. And I think what's really important with flow is not to think of just graphs, I suppose. Flow is more about relationships between things than anything else. And this often trips people up a lot. Flow is about defining relationship between different things and seeing where they overlap, I suppose, or where they like block each other out, I guess. So we're going to take a look at this question. Also, one other thing about flow is that you never have to mess with, I don't want to say never, but it would be highly unlikely and make the problem extremely difficult if you ever have to mess with the if you ever have to mess with the algorithms themselves. So whether that be Edmonds COP or like you won't have to touch the algorithms. You can just black box the algorithm, and it's always like I need to construct the flow network in some way such that this algorithm solves my problem. It's never like I want to change the algorithm to solve my problem. Yeah. Sorry. In a highly unusual turn of events, a signal failure has caused all trains across the entire Sydney Trains network to be halted immediately. Commuters are now stranded across the train network, with some being stuck at stations, while others being stuck between stations. Anyone currently at a station must stay where they are. Others are on trains in between stations. Oops, sorry, I read the wrong sentence. Since the trains are not moving, commuters who are currently on board a train need to exit immediately and walk either forwards to the next station or backwards to the previous station along the current section of track. Note that they may not walk past the station on the way to some other station, like they have to go to the next station. However, every station has a maximum occupancy to prevent safety issues that arise from overcrowding. Okay. So, therefore, any commuters who cannot go to either the previous station or next station will remain stranded, in the trains, and they'll need to be rescued. There are end stations with maximum occupancies and also current occupancies given in arrays A and B. There are M halted trains, each stuck between a pair of stations, given in arrays, I think it's X and Y, and carrying a number of passengers given in array P. Okay? Design an algorithm which runs in O of m plus n cubed time and determines the smallest possible number of commuters who will need to be rescued. The input consists of the positive integer n and arrays A and B of n integers each, where bi is between 0 and ai. That is just to say that my current occupancy can't be less than 0, can't have negative people, and also I can't have more people than my full capacity. As well as the non-negative integers m, negative integer n, arrays x and y of m integers each, where the jth train is halted on the section of track between stations xj and yj. And hence 1 is less than equal to xj, is less than yj, is less than equal to n. and an array P of m integers. So let's just look at an example. For example, suppose there are 3 stations whose maximum occupancies are A is equal to 453, currently holding B is equal to 332 commutes. Suppose that the rest of the input specifies m is equal to 2, and the arrays x is equal to 1, 2, y is equal to 3, 3, and p is equal to 5, 1. This represents one train being halted between 1 and 3, carrying 5 passengers, and the other halted between stations 2 and 3, carrying 1 passenger. So this diagram here. I'll give you a second to look at it. And I think this question feels really flowy if you like built some intuition for flow. Like we have like capacities, like this just makes you think of flow, right? And also one other thing, if we go back, sorry, I'll come back to that in a second, real quickly. The time complexity. If you get strange time complexities like m plus n all cubed, likely to be flow. It's possible that it's dp. It's unlikely. Like if you get larger time complexities, like n squared, n cubed plus, it's oftentimes like if it's n cubed, it's oftentimes it'll be flow. It could be like 2 parameter dp with like linear recurrence, something like that. I doubt they'd give you a 3 parameter dp. They could, but that would make it pretty difficult. Yeah. Because we do want to remember that Ford Fulkerson runs in EF time, right? Which is like n squared but not polynomial, whereas Edmonds Karp runs in n squared m. And this is essentially kind of cubic in a sense. It's really important to look at the time complexity. It really helps you understand, okay, what paradigm am I under? And also what algorithm am I using? So we'll go back to this image. Yeah, so does anyone have any ideas about how we can construct a flow network to solve our problem, I guess? Yeah?
Define stations as vertices, define trains as edges with capacity being the station's capacity and the flow being the train's passenger minus the train's passengers minus the car capacity of that station. And that would work.
I think that may work, but I'm not like 100% convinced, but that might just be me.
Now the flow might be changing.
I'm not 100% sure, to be honest. But this is not the solution, not the intended solution at least. It is possible that there are multiple solutions, but I'm not 100% sure it will work. I'm not sure it will work. The solution we're going to use is, this is essentially like the very prototypical sort of flow network you construct. I have a source, I have a sink, I have this sort of a bipartite graph in the middle, where the left-hand side represents something in my problem, the right-hand side represents another thing. So we have the left-hand side vertices represent trains, and let's say the right-hand side vertices represent stations. We have a source S and a sink T, where S is on the left-hand side and T is on the right-hand side. Connect S to each train vertex I with capacity equal to the number of passengers carried Pi. Okay, so essentially we have, I guess, our passengers coming in from the left and to these train vertices. And then we connect each train J to its neighboring stations Xj and Yj with infinite capacity. I guess some intuition for why it would be infinite here is because like as many people can run from the train to the station, only inhibited by the capacity of the station. So like, I guess they could all just wait outside the station, like, but they would still have to be rescued, I guess. And how do we represent this final part, which is the capacity of the train station? Which is to connect all of the train stations to T, all of the train stations to the sink with the corresponding capacities. So this is for our example previously stated. This diagram here. This is the exact flow network we would construct. So you see we have train 1, train 2, station 1, station 2, and station 3. We will connect the source to the trains, and then the trains to the stations, which are either directly in front of it or directly behind it. So like the one is between. So train, you can see train 1 is connected to station 1 and station 3 with infinite capacity. And our source we connected to our trains corresponding to like the amount of people they have, 5 or more. And finally, we have our stations connected to the sink by this value here, which is essentially the remaining capacity of the station. Yeah. So you can see how this kind of represents like, okay, here are the people, and here are like how many of them can fit in the stations, I guess. I'll give you a second to take a look at this. Okay, happy with that? So, what we now do on this flow network is we run Edmonds COMP. Yeah, we run Edmonds COMP because I guess we're given, yeah.
Short question.
Sure.
Instead of infinity, can it be the remaining capacity at that station?
The remaining capacity at that station.
Because you can't send more than that. to that
Because
station.
two trains can be connected to one station.
Yeah, multiple trains can be connected to one station.
You still won't be able to send.
Yeah, but let's say, let me think about this. We connect trains to the station for you. Okay, imagine we connected train 2 only to station 3, and train 2 was not connected to station 2, yeah? And we made, like, this capacity, both of these, A3 minus B3 is equal to 1. Imagine we send 1 through here from, okay, imagine we'll send train 1, send this guy from 0, 5 to 1. Seems to work. Yeah, it seems to work. Because that wasn't the case I was worried about. But yeah, that seems to work. We run Edmonds COMP. What does the max flow here represent?
Number of passengers who made it to a station, who made it, who don't need to be rescued, number.
So it represents the number of passengers who can be sent to stations. Yeah?
Don't need rescued.
Yeah. So hence, the number of passengers who need rescuing is the total number of passengers less the flow, less the max flow, I guess. Yeah? Because this is all the people that are still left on the train. The total number of people minus the number of people who made it to stations is the number of people we need rescue. So the time complexity of Edmonds COMP is of min v squared e and EF. But for your purposes, you can just assume that it's all v squared e, I'm pretty sure. And for our graph, we can think that we have how many edges? How many vertices? We have a source and a sink. We have a vertice for each edge in each train. That's 2 plus n plus n. Yeah? And how many edges? Well, we have an edge from the source to every train, and an edge from every train to the sink, that's n plus n. And then every train is behind every train is between two stations, so that's where we get our 2m from. Does that make sense? And finally, we just like plug these in. We can forget the constants, we can forget the constant multiplies as well, and that will just be m plus n squared times n plus n, which will be O of n plus n cubed, because like any other terms will just disappear by our big O. Does that make sense? Next, we're gonna look at dp. Actually, I think we should take a food break because the food's here now and we're also about an hour in. So we'll take a break. There's pizza. Feel free to take some. Yep. And if you have any questions, you know. Yep. Yeah, we'll share it here on the Discord and if you want to yeah, so we have this question, let S be a sequence of integers. We define a tribus in S as a triplet of consecutive sequence elements whose sum is a multiple of 3. For example, if we have this S up here, then all of the tribuses are highlighted below. So we have this first 1 for 1. This adds up to 6, and we have 159. This adds up to 15, and 537 adds up to 15. This is a little bit misleading because they're all like exactly consecutive, and it's not a consecutive subarray, but rather a consecutive sequence. So I could have like, I don't know, like 2, 3, 7s. I don't know, something else that it doesn't have to necessarily be just connected right like that, I guess. Because my subsequence could include like a 1 or something, I don't know. And a sequence A is said to be more tribusy, so once again it's a sequence. A sequence A is said to be more tribusy than a sequence B if A has more tribuses than B. So given a sequence of n integers S, we want to describe an O of n cubed algorithm to compute the number of tribuses in the most tribusy sequence of S. Yeah, so this question is quite tough, but have a think about it. But also, you know it's DP. And with DP, there are like 2 things that affect the time complexity of the algorithm. One is the number of parameters, and 2 is the time complexity of the recurrence. So if I have something that's n cubed, it's possible that I have a 3-parameter DP, alright? A 3-parameter DP where my recurrence is constant. I could also have a 2-parameter DP where my recurrence is linear, or perhaps even a 1D DP where my recurrence is n squared. But I'm not sure about that because if you have only like a row of things to select from to look at, why would you have to look at it n squared times? But yeah, have a think about it.
So here the subsequence would be 1, 4, 1, 5, 9, 5, 3, 7, 8,
1, 4, 1, 5, 9, 5, 3, 7.
and that will have 3.
Yes, yes. I think we have an exact example here to help you out a little. So we have this new S, this is different. This should return like 4, because the most tribusy subsequence is going to be S prime, which is 0, 1, 2, 3, 8, 13, 21, which has the following 4 tribuses. 0, 1, 2, 2, 3, 8, 3, 8, 13, 8, 13, 21. So like you can see, like for each tribus, there might be like other things that are not in that tribus, but still in the subsequence. And you can see that there's 4 tribuses in here, and this is the most tribusy subsequence of S. Does anyone have any ideas about how maybe we can solve it? Just spit it out. Yeah, sure.
For row and for column, I think we can have
Sorry, could you speak be a bit louder?
For a teaching table, I think we can have like for column, we can have the items in the sequence, and for the row, I think we can have the number. For example, like 3, 6, or something, and then we can make subtract the number by each end, so that's 2 by 2 by 2 by 2. And then if the number came back to 0, then it's gonna be it is supposed to set up the target number one to register for example DPI 6 is that can be done, then it would be possible, so we can have like set up the number in the J.
In this, what is your sub-problem here? Because it's good to be thinking about the DP table and to be forming a recurrence, but it's really important that we could define different sub-problems, right? Like we could say that sub-problem is the most tri-bar C, let's call like our sub-problem the most tri-bar C subsequence of like S ending at some number I, at some index I. Like we could define that. We could even define it as like between two numbers, and this would all lead to like different recurrences between them, and possibly a lot of them may not work. So my question is like, what is your sub-problem in that case?
So I think for sub-problem, I think the DPIJ, which is which would be is this the counting the possibility or?
Yeah, we only need to know the maximum number. Yeah.
So,
In the most tri-bar C sequence, so like, yeah.
so I think we can record the what's the maximum number, and then this time for even it's like sum, so even the maximum is limited to the all the sum of the elements in the sequence. So we can have that in the for J, and then so that we can take DP, so we can take the subproblem of like DP I, which is the item number, and J is the sum.
Yeah, I think you're somewhere along the right track there. I think so. But I'm not sure that it's the exact solution required. Let's take a look at that. So you may have thought about a couple sub-problems to define. And by the way, for every DP problem, you want to answer in like this sort of format where we have the sub-problem, the recurrence, the order of computation, and the final solution, and also our justification, of course. So we'll have to have those parts, and we'll start off with our sub-problem. So let's just first say it. For each 1 less than equal to I, less than j, less than equal to n, let dp of ij denote the number of tribosses in the most tribossy subsequence of ai through n. This is not, so essentially we're starting at I, and we're looking at the subarray, I guess, through to the end, whose first two elements are AI and AJ. This is really important, and this is actually really hard to find, that we need the first two elements to be AI and AJ, because you actually have a lot of things to try before you get to here, like starting at just AI and ending at AJ, something like that. But for a lot of reasons, which we can't go into like every single case, but you will find that it doesn't quite work. You can take a look at this question, like in your own time, really grapple with it, like the slides will be up at some point. Yeah, but you will come to realize that you need the first two elements to be AI and AJ as part of your subproblem definition. Firstly, just to simplify notation, we will define a function tribus ijk that returns 1 if and only if AI plus AJ plus AK is divisible by 3 and 0 otherwise. So I guess you can just think of it as an indicator function. That just returns 1 or 0. Oops. Next, for our recurrence, assuming that AI and AJ form the first 2 elements of a tribus, we need to compute when the last element of the tribus appears. Right? So therefore we check if AI, AJ plus AK is divisible by 3 for some j less than k less than equal to n. So our k needs to be after ij because ij are the first 2 in our subsequence, I suppose. So k has to be somewhere after. But it also can't be past like the original sequence array. And this gives the recurrence that dp of ij is equal to the maximum over tribus of ijk plus dp of jk for every j between, for every k between j and n. And remember, this tribus is just returns 1 or 0. 1 if ijk forms tribus, 0 if not. Now you probably not too sure about this, might not even believe this, no reason to. Maybe you can have a think about it, try to convince yourself. But this is going to be our recurrence. And also, yeah, I forgot to mention, one of the other parts is the base case. And you want to go in this exact order as well. So I guess what is our base case? Well, if we think about how we defined our subproblem, if ij are the first 2, if j is the last one, then there can't exist any tribuses because there's no j after it that's also in the array. Right? Does that make sense? So dp of in would just be equal to 0 because there's no tribuses in it. These things only have 2 elements in it. No way you can form a tribus. And here's our dp table, by the way. So we have dp of I from 0 through 7, and j from 0 through 8. I didn't include the 8th row for I, simply because of the fact that I is strictly less than j. So like it wouldn't really make sense for there to be an 8th index for I, because then what would j be? And it doesn't really matter, because I guess either way we would define it as 0 tribuses. Does that make sense? And you can see all along our, I'll move my cursor out the way, all along our right side, we have zeros. And this is our base case. Okay, let's try to calculate dp of like something, but let's do 6j, and especially 6, 7. If we look at this, dp of 6, 7 is max over this, right? And what does it depend on? Well, it depends on everything of dp that starts with 7, right? dp of 7 something k. But the thing is, k is also strictly greater than j, right? And if j is 7, what does that mean k has to be? Well, it has to be 8, right? K has to be 8. So it depends on dp of 7, 8. Specifically this square right here. So this depends precisely on this, and whether or not I guess the kth element and ij form a tribus. I should move over a little bit more, hopefully. So now, this is our sequence, by the way. It's like the previous one we were looking at. So if we look at 6, 7, 8, do they form a tribus? 0. No, I mean, it should just be calculated for me. It does, yeah, 21 plus 42 divisible by 3. So you can see that this square here is dependent on this square, and then some other thing, which is our tribus. And there is one tribus here. We look at the next square, dp of 5j. Okay? dp of 5j, we'll be looking at also, it just happens to be 5, I guess. So 5, 13, and then the only thing after it can once again only be the 8th element, which is 21 in this case. So I guess we're asking ourselves, does 18 plus 21 give me a division by 3? Yeah, it does, 39, right? Does that make sense? And for, like, I would say this row, this column here is not particularly interesting because there's only one value k to b, right? And by the way, from now on, oh, green is what we're calculating now. Oh, yellow is the dependency of what we're calculating. Okay? So for this one, we'll keep going. We find that, I guess 3 plus 13 plus 21, 34, 37 is not divisible by 3. So once again, we have nothing here. There are no tribuses in this location. And then eventually we do this for every column. The second column gets more interesting now, right? Because we now have two dependencies, because k can be both 7 and 8 now, right? We've moved to the left of it, we have this space now, such that k can be 7 or 8. Firstly, we can no longer have this dp of 6, 6, because once again, I is strictly less than j, right? So we look at the next thing, 5, 6. Now what we have to look at is if 5, 8, 13, 5, 8, 13, and also 5, 8, 21. Yeah? And this now depends on these two things as well. 6, 7, and 6, 8. And we want to see what the maximum here could be between taking this one and this one. Now if we take this one, we have 5, 0, 1, 2, 3, 4, 5, 6, 7. So 5, 8, and 13. Those are the elements we're taking. This gives us 26. So that's no tribus. So the tribus part gives us 0, but the dp part, this one does give us 1. So hopefully this says 1. Yep. This says 1. Now, the reason we already can say that is, well, this is 0. Tribus can at most give us 1 more. So the maximum has to be 1. Right? Because even if this thing does form a tribus, which let's say 5, 8, 21 does, 34, it doesn't anyway, but even if it did, it couldn't be any more than 1. Does that make sense? We keep doing this. Now it's 2, it's 1, and so on. And then we look at the next column. Now, k can be 3 different values. It can be 6, 7, or 8. And we have all of these dependencies, right? And can you see what's starting to happen? How many dependencies do we have each time? Like, what is the order of our dependencies?
Linear.
Yeah, it's linear, right? Because I hope you can imagine when we reach like the end of this sort of a staircase, the yellow will like come across the whole thing and will be order O of n. Yeah? Does that make sense? This happens to be 2, this happens to be 2, and this is what the whole thing looks like. Hopefully I haven't made a mistake. It doesn't seem so because the maximum is 4. Yeah. So I have a question. What should our order of computation here be?
Could you repeat that?
Sorry?
Could you repeat the question? Like, what
Oh yeah, sure. What will our order of computation be here? What is the order of computation that works for us that lets us solve the problem?
You mean the time complexity?
Sorry?
You mean the time complexity?
Not the time complexity, the order of computations, which is in which order do we want to compute our subproblems, essentially?
Is it decreasing?
Like, so how do we want to traverse these squares?
Decreasing I and J.
Decreasing order by j? Yeah. And this, you can see with the dp table, it's really obvious, right? Because we're going from the bottom right to the top left. This is obviously decreasing order by j. And the reason we have an order of computation is, well, like imagine we started there, like in the top left, these things would not be calculated yet. Like, imagine we started at dp of 0, 1, well dp of 1, 2 wouldn't be calculated yet, but it depends on dp of 1, 2. We're screwed, right? We're screwed. Yeah, so that's why we have the dp of, the order of computation is essentially so that when we calculate the dp, we know that everything that we depend on has already been calculated. Okay? Now I have another question. We know that the recurrence is linear, as you said. How many? What is our subproblem? Like, what is our order of number of subproblems? Yeah, n squared. You could have guessed this because like this is the solution and our recurrence is linear and our solution was n cubed, so like I guess you just fill in the gap, it's n squared. But also, like you can see, like these are each one of these numbers represents a subproblem we've had to solve, right? And you can see like that this is like this step thing, this like pyramid, like it's famously an AP, which is like n plus 1 or 2, and that's n squared, number of subproblems.
Yeah, it's basically like we're just fixing the first two elements on the triangles, right? So that's n choose 2.
Yeah.
Which is this.
Yeah, you can think of it like that as well. Finally, we have the order of computation, as you guys said, makes sense, and time complexity makes sense. And really, every time you answer a DP question, you want to have all of these parts. All of these parts from my subproblem, my recurrence, my base case, order of computation and final solution, and then my time complexity. This is the exact structure you want to answer your question. Yep. And this is also how you want to think about it. The first things you want to think about are what is my subproblem? Does this subproblem give me a recurrence that works? And then once that works, you just have to figure out, like everything after that just follows. Yeah. Sure. What's your question?
Do you have any intuition on how to come up with the subproblem?
Yeah. There are a lot of like sort of common ones, which is like, oh, I solve the, like for example, do you know LIS? Yeah, like that subproblem is, okay, the LIS up to this index, and then there will be a lot of ones that are also the subproblem between these two indices. That's also a very common one. Also the subproblem starting at this index, right? That's also another really common one. The reason I said this was hard is simply just because this subproblem definition is very uncommon and very specific to this question. But I would start there. When you're sure those do not work, it must mean two things. Either you're missing something to the question, and you kind of want to develop your intuition from there, or two, you're missing a parameter. If you're missing a parameter, you simply just don't have enough information. And then the third case, worst of all, I suppose, is this might not be a DP problem. With these questions, I think the divide and conquer is usually relatively obvious. So I would say so is greedy, because like I feel like everybody tries a greedy initially, right? For everything, if it doesn't work, it doesn't work. The thing that's really complicated is like, sometimes it could be a flow network, or it could be a DP question. Because you both have these things where different parts of the problem depend on other different parts of the problem as well, for both of these. I would start with like those like most basic like DP definitions. If those don't work, I would go on from there. And I guess there's no better way to develop your intuition than to just do a bunch of problems.
If I could add to that, so
Sure.
here it's a triplet. So 3 variables that sum up to a multiple of 3.
Yeah.
So the DP will always have states which is equal to the number of parameters minus 1.
Yeah.
So we need to fix at least 2 and
Yeah.
move through for the third one. So that's how we get like an n squared DP with a linear recurrence.
Yeah, that absolutely makes sense. Yeah. Okay, I hope that made sense to you guys. I hope with the DP table, it's like you can really see exactly what's happening with the illustration. But we're going to move on now to your final topic, which is, I don't know, is it called interactability? Like, I think it's called interactability, but I guess the name doesn't really matter. We're going to start off with some theory here. This will be like relevant in your multiple choice and also like proving of the question. So for problem U, it's said to be NP if it can be solved in non-deterministic polynomial time.
Sorry, isn't NP verified?
Sorry?
NP doesn't NP can be verified in polynomial time?
That's also true. These two are actually exactly the same thing. I can get to that in a second, but those two definitions are actually exactly the same thing. So for your purposes, like this non-deterministic polynomial time kind of is like, it's hard to understand, sort of. But for your purposes, like you can just assume that it can be solved in polynomial time. It cannot be solved in polynomial time. That's not like precisely the definition, but it's like good enough, right? It's like if I see O of n cubed, okay, this is p, or I can solve this in polynomial time. If I see like some sort of exponential, then okay, no good. And then we have this other thing, is a problem V is said to be an NP hard if every NP problem can be reduced to it. I hope you've heard the idea of reductions at this point, but we'll get more into it. And basically, the general gist is that NP hard problems are at least as hard as every single NP problem. This represents the problems that are at least as hard as all problems in NP. So finally, if V is also NP, so before it was NP hard, now it's also NP, then we can say that it is NPC, NP complete. Okay? To get to your point before, I'll address it right now, but to say that it can be solved in non-deterministic polynomial time is essentially to say that if we go through the tree of like the solution, I look at every branch at the same time. That's what a non-deterministic algorithm, like non-deterministic computer can do. I can look at everything at the same time, but this doesn't really mean anything to us, besides the fact that we know that the answer is true. Because like we can only see the end essentially, because like the middle is sort of black magic is what they say. And this is equivalent to saying that it can be verified in polynomial time. Does that make sense? Move on. This is like your basic diagram of problem complexity classes. Here we have P, which is P algorithms. It can be solved in polynomial time. We have NP, which can be solved in non-deterministic polynomial time. We can see that P is actually a subset of NP. The reason that this is dotted is because, well, famously, we don't know if P is equal to NP. And then finally, we have this where the intersection of NP hard and NP, we have NP complete. Now, very importantly, not every NP hard problem, actually not too important to you, but not every, not too important to you, but not every NP hard problem is NP complete. So you have a problem like the halting problem, which is famously NP hard but not NP. But a lot of the things you will look at are NP hard and NP, and so they're NP complete. Okay, here's a question. Here's a multiple choice question, I guess. Assume that P doesn't equal NP. Consider the following pair of decision problems. So we have 3 coloring. Given a graph G, I hope you've heard of these problems before, like 3 coloring and forests. I think in your exam you'll be given a list of known NP hard or known NP complete problems, right? Because you need those to reduce from, or reduce to, I suppose. So given a graph G, defined by its vertices and edges, is it possible to color the vertices of G using at most 3 colors such that no pair of adjacent vertices share the same color? So this means for any two vertices in the graph, if they're next to each other, they're not the same color. Okay? Finally, we have forest. This isn't an NP hard. Like, given a graph G equals to VE, does G contain no cycles? Okay? How can we solve this in P time? Anyone?
Consider all subsets.
What do you mean by that?
All subsets of the vertices graph, and for a given subset, you can just check if it is a cycle.
Yeah, how do you check if there's a cycle?
Start from one node, keep going if we end up back.
Yeah, that is the idea, I guess. Yeah. So we can use DFS cycle check. Yeah. You guys know we can use DFS to check for a cycle. So if we ever encounter ourselves again, then of course there's a cycle when we DFS. Hope you've heard of that. So we know that forest is solvable in P time, and we have three coloring, which is actually a known NP-hard problem. Okay. We want to select which of all of the following statements that are true. Which ones here are true? I'll give you a second to think about it. Okay, do we think, I guess I want, do we think I is true? Yeah, we can use DFS cycle track. Do we think I is true? Does anyone think I is true? I mean I is true? No? Do you guys think it's false? Do you think it's false? Forest and three coloring is P. Okay. We'll get to that in a second. Forest or three coloring, that's P. What do we think? False? That's false. Okay. Why? Well, why is it false? Three calls NP hard? Yeah. But does forest affect it in some way? Maybe. Like, could it conceivably affect it in some way, and why does it not? I guess. Well, because it's like or, right? Like we could just assume, let's just assume forest is true. False, right? Now we have the problem of deciding, we still have to just decide three call, right? It's the same thing, because this, or if this is a 0, and this could still be a 0 or 1, well, it can still, the whole thing can still be 0 or 1, right? So we are essentially left with just deciding three call, once again, is NP hard. Okay? And part 4, a polynomial time algorithm from three call to forest would imply P is equal to NP. Do we think this is true or false?
Sure.
Yeah. So if we can solve this P problem, if we can solve this P problem and we can turn this P problem into this NP problem, NP hard problem actually, in P time, well then P is equal to NP. Okay, the second one is a bit more interesting now, because it's intersection. Yeah? Let's say conceivably forest was 0, right? Then the whole thing is just immediately 0, right? Now the problem is if forest is 1. Three call, it still depends on three call being 1 or 0. Here's the thing. If forest is 1 or true, what does that say about our graph? Doesn't have some. What kind of graph is this?
Basically.
Acyclic, sure.
Tree.
Sorry? There are no other constraints on V or E. Yeah. I think I heard you saying something that like might be correct.
A bunch of trees.
Yeah, so it's either a bunch of trees or I guess it's just one big tree.
Yeah.
How is this useful to us in terms of three coloring? Anyone know?
We can split it into levels, and each level can have a different color.
Yeah, that's a very good way of thinking about it. So that is to say that all trees, and therefore all forests, because forests are just made up of trees, all trees are three colorable. Because if you think, I don't know if I have a marker, but, oh, do you have one?
Right.
You know what? Honestly, I'm gonna make this one.
Just roll it down.
Oh yeah, I can't show it down. Whatever. It's light, so good enough. Like, if we think of we have some tree, right? Can you guys see this, by the way?
Wait, do it a bit lower so the camera can see.
A bit lower.
They're like right a bit lower.
Here, can the camera see here?
Lower. Yeah, that's good. And then
Okay.
just make the writing big.
Imagine this is my node, like some node of a tree. This is another node of a tree. This is another node of a tree. These are the nodes of the tree. Like, you can think of the tree in levels. I guess this would be a level, this would be a level, and this would be a level. I can just color each of these levels a different color. So, in fact, not only is it three colorable, it's two colorable. Alright? So you can see that if it's an intersection of a TP and NP problem, it's not so simple. Yeah? And there might be something you need to think about. Okay? Does that make sense to you guys? I'll move the screen if you want now. Well, I think, okay, I think there's a slide missing. That's interesting. There is one thing I need to talk about before we do this, is the idea of a reduction. But you're probably already familiar with this. Let's see if I can get this right. If I can reduce problem U to problem V, this means problem V is at least as hard as U. Yeah, I think that's right. Yeah. I'm sure everyone understands that. Like, it makes sense, but it's like easy to mess up. Like when you say it in the exam, just make sure that like it really makes sense. It really makes sense because it's not like honestly easy to mess up. It's really easy to mess up. And essentially, we know that we can reduce all NP problems to like NP hard, right? We already know that. We said that in the previous slide. Here is a problem called balloon graph. So a balloon of size k is an undirected graph that consists of a simple cycle of length k and a simple path of size k, where the path contains an endpoint that lies on the circle. Every other vertex on the cycle is disjoint from every other vertex on the path. A balloon of size k and 2k has 2k vertices, k vertices in the cycle, and k plus 1 vertices in the path, including the endpoint in the cycle. So like, there's k here, but including this one, that would be k plus 1. Like, all of that is just a really mathematical way of just saying that the graph looks like a balloon, basically. Yeah, so figure 1 shows balloon cool. Given an undirected graph G, prove that it is NP hard to find the size of the largest balloon subgraph of G. Here's our problem. Prove that it is NP hard. How can we do this? How do we prove something's NP hard? Yeah?
We reduce it to a low NP hard.
Yeah, exactly. That's exactly correct. To show that finding the largest balloon subgraph of G is NP hard, we need to reduce from / to a known NP hard problem and vice versa. We need to show that they're equivalent essentially. In your lectures, you may have seen this as being said that every zero case maps to, from one problem, maps to a zero case of the other problem, and every one case maps to a one case of the other problem. That shows that these problems are like essentially equivalent. Okay, does anyone maybe have an idea of a known NP hard problem that we can use? No? It's fine in the exam, I think you'll be given on this problem. But in this case, Ham cycle, Hamiltonian cycle. Do we all know what a Hamiltonian cycle is? Yeah, I'm going to assume. So, a Hamiltonian cycle is simply a cycle in a graph where I visit each vertex one time, but like I end where I start. And it has to be a simple path. So like, I can't go back and forth between the same one. I can't go like, I can't revisit the vertex same time. I only visit each vertex exactly one time. And I end up in a cycle. So I guess like if you cut off this bit and you only have that, I guess the balloon part of the balloon, it's a Hamiltonian cycle. So can we see how that might be related to this problem? Right?
To find a balloon subgraph, we need to find at least a Hamiltonian cycle.
Yeah, that's true. Like part of the balloon subgraph, like subgraph of the balloon subgraph, has to at least contain Hamiltonians. Has to have a Hamiltonian cycle graph. Right? Because otherwise we don't have the balloon part of our balloon. Here's the solution, and when we're asked to answer a question like this, just follow this format, always. We reduce from the Hamiltonian cycle problem, let G is equal to VE be an arbitrary graph. So it's important that it's arbitrary, and let N denote the number of vertices in G. We construct H by adding a path P of length N to this, to an length N to an arbitrary vertex X in G. Okay? And here's the important part. We claim that G has a Hamiltonian cycle if and only if H has a balloon of size N. And this is really, really important because this means that every zero maps to a zero, every one maps to a one. Both ways. Because like you could like A implies B doesn't necessarily mean B implies A, right? Hope that makes sense there, Ron. So we need to go both ways. And to go both ways, we have to prove both ways. And here's the forward proof. Suppose that G has a Hamiltonian cycle C. This cycle passes through X and is of length N. Yeah? But remember, we added P to the graph. So C union P, this is probably a bit of abusive notation, but essentially the vertices in C union the vertices in P, whatever the graph that forms, this must be a balloon of size N. Does that make sense? Yeah? And we have to go the opposite way as well. Suppose that H has a balloon of size N. This graph is I guess this was what you were alluding to before. This graph is a union of a cycle C and a path P, both of lengths N. The cycle cannot contain any edges in P, so C must lie entirely within the original graph, right? Because the P we added on was a path. This couldn't possibly, and it's only connected to my original graph at one point X. This couldn't possibly form part of my cycle. Yeah? So if I find that there's a Hamiltonian, cycle on H, then G has to have the Hamiltonian cycle. So the cycle cannot contain any edges in P, so C must lie entirely within the original graph. Therefore, C must be a Hamiltonian cycle. And yeah, we also need to, I guess, show the reduction can be done in polynomial time. But of course, like changing the graph, adding like n vertices, of course, is n time. This is perfectly fine, right? Does that make sense to you guys? Like, there is feasibly a case where I add like 2 to the n vertices, and like this process of changing one problem into the other runs in like, it's like non-polynomial. So then we don't know what's causing the NP-ness, essentially. It could be like my changing of the thing, or it could be like my actual algorithm. This is it. How are we going for time? 3:52. There are some extra questions if you guys would like me to go through, which I think some of them may be interesting, particularly the first one. Yeah. I'll just let you know that this question does involve divide and conquer, and it also does involve, I guess, sort of in a way, greed. It sort of mixes the two. So soon there will be held the world's largest programming contest, but the testing system still has n bugs. The contest organizer, a well-known university, had no choice but to attract university students to fix all the bugs. The university has n students able to perform such work. The students realize that they are only hope of the organizers, so they don't want to work for free. The other student wants to get CI passes in his subjects, regardless of the volume of his work. Sorry, I'll just drink some water. Bugs, like students, are not the same. Every bug is characterized by complexity AJ, and every student has the level of visibility is BI. Student I can fix a bug J only if the level of visibility is not less than the complexity of the bug. So essentially, like, if he's at least as competent as the bug, he can solve it. And he does it in one day, otherwise the bug will not be fixed by another student. Of course, no student can work on a few bugs in one day. All bugs are not dependent on each other, so they can be corrected in any order, and different students can work simultaneously. The university wants to fix all the bugs as quickly as possible by giving the students a total of not more than S passes. Determine which students to use for that, and come up with the schedule of work saying which student should fix which bug. So I'm given my A's, my B's, and my C's. Yeah, and also my number of bugs and students, and the number of passes I'm willing to give out. If the university can't correct all the bugs, print no. Yeah, okay, like we just want to decide whether or not the university can fix all the bugs. The bugs should be corrected as quickly as possible, so we want to minimize the number of days, and the total given passes mustn't exceed S if there are multiple optimal answers. Okay, this doesn't matter, but essentially what we're trying to do here is we're trying to minimize the number of days, but also the number of passes given. Oftentimes when you have something where you're trying to minimize / maximize, find the optimal of both things, what I wanted you to realize is that oftentimes you can binary search on this. You use a binary search to turn one of these optimization problems into a decision problem. Yeah, and this is just the main point I wanted to get across with this question. You can try a lot of things in this. My first intuition, maybe your first intuition, is to sort the bugs in decreasing order of complexity, and also the students in decreasing order of ability, right? So then we can assign like the best person to fix the hardest bug, and so on and so forth. This doesn't quite take into account cost, right? So perhaps we say we want to take the best person who can fix the bug for the cheapest price. So imagine I have a complexity of a bug of 1, and then I have 2 people who have abilities 2, but one of them has a cost of 3, the other one has a cost of 6, I'm going to take the guy with cost 3. This makes sense, right? The problem now is that I need to minimize the number of days as well. So, for example, if I now had, I guess, 2 bugs, something, yeah, 2 bugs, same people. I don't know whether the second person should like we know the second person should do it today, but like it's not optimal, right? Because imagine if the second person didn't have the correct ability to do it. Yeah. So one thing you might try here is to say, okay, let's just make the best person solve like as many of the bugs as they can, right? Because we know, like we've already used this guy, this minimizes the cost, right? We've already used this guy, so now he is like free. We can keep using this guy. The problem here now is that, well, I don't know the number of days. Like theoretically, if I knew the number of days that was optimal, I could just say, okay, this guy does this, like the hardest bug each day for this many days. Yeah? Problem is I don't know the number of days. Here's the important part of where binary search comes in. I'm going to say I binary search on the number of days instead of optimizing for the number of days. And for each day, I say, okay, can I solve the problem in this number of days? If I can, well, I know binary search down to lower days, right? And each time I just need to give every best person the number of days, number of bugs, right? And then so on, from the highest ability person to the lowest ability person, right? Does that make sense? Yeah? And then eventually when my binary search ends, a binary search on the number of day ends, I will hopefully have found, well, I will have found whether all the bugs can be fixed with a given number of passes, or they can't. Yeah. This question is pretty difficult, but it's just to demonstrate the fact that if I have 2 things that I need to maximize or minimize, maybe the solution is to binary search on one of them. Because I know the first question was really, I would say, is quite obvious, given the log n, and also given the sort of the nature of like finding something along that line is like very binary searchy, but binary search is often hiding in places where you don't see it. Yeah. Like this is kind of similar to, I don't know if this is a question in yours, but I believe it is, but it might be like an HD question, just like flowers in a garden. Not a problem. No? It is a question? Yeah, it might be like an HD or D question. But essentially, like you're sort of trying to optimize in 2D. You can think of it like that. You're trying to optimize the Y and optimize the X. And you remember you wanted to binary search in one directions. Yeah, okay, that's it. I guess I can keep going. This is a flow question. This is also a very difficult flow question. Whereas I feel like, here's the thing, flow can be hiding in places you don't necessarily expect it. Like the previous question seemed pretty obvious to be flow, in my opinion. But this question is nowhere near as obvious. Yeah, you can, by the way, you can leave if you want now. Yeah. This question, take a read. It's not as obvious. So it says design a p-time algorithm which determines the maximum number of knights that can be placed on undamaged squares such that no 2 knights attack each other. Is it surprising that this is a flow question? You guys think? Yeah? It is to me, like it's pretty unintuitive. And you may have seen a solution similar to this and like, I don't know, if you've done like a column question before, like you may have seen something like this. Separate the grid into 2 parts. The ones which are white and the ones which are black. Clearly, because we know that knights can only attack opposite colored squares, right? Clearly, if 2 knights attack each other, they are in opposite parts of the grid. We need to find the maximum independent set of vertices. One in which no 2 vertices in the same set are adjacent of the resultant bipartite graph. construct the flow network with the following. A vertex for each undamaged square in the grid, an edge with capacity 1 from a white undamaged square to a black undamaged square for each pair of undamaged squares such that two knights placed on them would attack each other. Yeah? So this idea of separating into white and black. Then we have a supersource from which there is an edge capacity of 1 to each white square, a supersink to which there is an edge capacity of 1 from each black square. Run Edmonds COP on this graph to obtain F. This also gives you, I hope you know, the number of vertices in the minimum vertex cover, and the overall time complexity is polynomial, since constructing the graph and the Edmonds COP algorithm both take polynomial time. Precisely how much time it takes, if I have an n by n chessboard, it'll be n squared. I believe it'll be something on the order of like n squared, m squared, n, I believe, to run Edmonds COP. Yeah. Sorry, n to the 4. But it's just I'm just trying to tell you that flow questions can be really tricky sometimes. Hopefully, they won't be as hard as this, I'm pretty sure. 99% sure. Yep. Root 5, root 5 is just a mathematical way of saying like, the knight move. Because if you think about it, it moves like 2 in one way, 1 in the other. That's root 5. Yeah.
And the order of black and white from supersource to you could have had the black from supersource and white from supersource.
You can think, yeah, it doesn't matter. Because black and white is symmetric. And also you can think of the source and sink as symmetric a lot of times as well. Yeah. Okay, thank you everyone. Also, the slides will be on Discord. So, I would say by far the hardest two are DP and flow. Like, I wouldn't say 1/6 is difficult.